Okay, let's get started. What? Only 1, 2, 3, 4, 5 of us? Okay, yeah, maybe you should stop streaming the videos. Yeah, first of all, just a reminder, please start working on homework 3, I guess. The workload is light, but don't try to finish that at last day. That won't be sufficient. Okay. At the same time, please consider keep pushing the progress of your project, because we also need a final project report, and we need more, much more detailed results and conclusion. And for the final project report due, is very unlikely we are able to make an extension, because we have some like strict deadline to submit to the final grade. We cannot compromise on extensions. So yeah, just a reminder, if you have submitted midterm report but has yet done anything about the current project, please start going with that. We do want to see progress on a project. Okay, so let us continue with support back machines. So in the last lecture, we talked about how do we optimize the support vector machines learning objective function in the primal domain, right? And we said that in the primal domain, you're still estimating a linear classifier. But what if you want to perform a nonlinear classification? You want to generalize the capability of SVM to nonlinear classification problem. So we said that we're going to use some kernel trick. We're going to use some feature lifting trick. These are major focus of our discussion today and next lecture. So to enable such generalization, we start introducing the general framework that is a primal form and dual form for constraint optimization. Why do we want to introduce this? Because we're going to transform the objective function of the SVM into its dual form. And later we'll see that by modifying its dual form, it is very easy to inject the so-called kernel trick and feature lifting to enable flexible nonlinear classification. So that's the framework. So in the last lecture, we introduced for any constraint optimization problem, if we can write the objective function as f of x, and x must satisfy a set of constraints where each constraint can be represented by an inequality that a constraint function g1x less than or equal to 0, the second constraint function g2x less than or equal to 0 until the last constraint function gm of x less than or equal to 0. So this is called general constraint optimization problem. Here we don't put any assumption about the form of f and g. F can be convex or non-convex. G1 to gm can be convex, non-convex, linear, nonlinear, and so on. And then we claim that this general constraint optimization problem is equivalent to solving a minimax optimization problem. The objective of this minimax optimization is the Lagrange function. So Lagrange function is the original objective fx plus a linear combination of the constraint functions in the original problem, where each coefficient lambda I here is called a Lagrange multiplier. So if we try to solve this minimax optimization problem over the Lagrange function, where in the inner level, we maximize the Lagrange function with respect to non-negative multipliers. While in the outer level, I minimize the Lagrange function with respect to x. Then we can show that the solution of the original constraint optimization problem is also the solution of this minimax optimization problem, and vice versa. Right? So we're not gonna look at details why, because we haven't shown that, right? So the benefit of doing such a transformation is that by introducing these additional Lagrange multipliers, then in this minimax optimization, X is total free. You don't need to worry about any constraint about X. Right? X can be searched over the entire real space. And the only constraint is over the Lagrange multipliers, which is negative, non-negative constraint, which is relatively simple constraint, right? Which is also called box constraints. It is much, much easier than you solve the original problem where your feasible space are determined by a set of nonlinear inequalities, right? When G1x to GMX are complex and nonlinear, you even do not know what is the shape of the feasible space for X, right? But when you do this conversion, you introduce a minimax, that is a double level optimization problem, right? But you get rid of the complex constraint over X. You only introduce additional variables, lambdas, and very simple constraints, that is lambda must be non-negative, right? That's the benefit of using this transformation, right? And then we talk about what is dual form. So we call this minimax optimization over the Lagrange function as the primal form. And the dual form is just to switch the max, the order of the min and max. Namely, in the inner level, I minimize the Lagrange function with respect to X. Then in the outer level, I maximize the Lagrange function with respect to non-negative multipliers lambda. This is called dual form. Right? So you can see that primal form and dual form is very simple. It's just to switch the order of min and max. However, in general, once you switch the order, the solution of the two problems will change. And the general conclusion will be the optimal value of the dual form will be less than or equal to the optimal value of the primal form. More explicitly, if you solve the dual problem, that is max min, okay? You find the optimal X and lambda, and then you calculate the corresponding the Lagrange function value. It will be less than or equal to, you calculate the Lagrange function value with optimal X and lambda for the primal problem, namely solving the min and max. Okay? So we have listed the proof steps of showing that as is pretty simple, but we do not plan to go through that. It's just for your reference. Although in general case, solving dual problem is not equivalent to solving the primal problem, but in SVM, they are equivalent. In other words, in SVM, solving dual is equivalent to solving the primal form. Namely, you switch the order max min, it doesn't change the solution. Okay, this is what we have discussed so far. Any question before we proceed? We're on the same page, right? Okay. So as to why the dual form of SVM is equivalent to the primal form is mainly because the objective function is convex, and also the feasible region is super convex in that the feasible region at least have one interior point. That's why you can have such a conclusion, but it doesn't matter. We just need to know the conclusion that dual form of SVM is equivalent to the primal form. So next, we're gonna try to convert the primal form of SVM to the dual form and do some simple simplification and derive something and say what kind of dual objective function for SVM we need to solve. Okay, so this is the soft SVM objective function we have previously introduced, right? So the objective function is the half of the square norm of the weight vector. Remember, this is to maximize the margin, right? And also, we introduce a set of slack variables, remember, because in general case, we cannot assume that data is always linearly separable. The data could be nonlinear separable. In that case, we should introduce a flexible framework that we can exclude some points from the data and only maximize the margin for the remaining data points, right? And to allow such flexibility, we introduce a slack variable KCI, which is non-negative, and we add the constraint that for every training example, we have this function margin to be less than or to be no less than 1 minus KCI. So if KCI is strictly positive, then that means the function margin will be less than 1. Will be just, no less than 1 minus KCI, but 1 minus KCI will be less than 1. So that means the XI, that training point could be inside the margin or intrude the margin, right? That means, margin maximization procedure will first kick that example out and then look for the margin for the remaining data points, right? And meanwhile, because we do not want to too many training examples to be excluded or to allow them to break into the margin, so we add additional term here, which is summation of all the KCIs. So basically means that, okay, I want to minimize the summation. So that means I want to as few examples as possible to break into the margin. In that way, I still expect that I can correctly classify most of the training examples so that my training error is very small. At the same time, because I maximize the margin, my generalization error bound will be upper bounded by the training error plus some term determined by the VC dimension, right? You have a small VC dimension, you have a small training error. Overall, you have a tighter bound, right? If you don't add this one, right? If you don't add this summation of the slack variables, you can imagine a lot of examples are just the kickout. That means your training error could be large, right? Although your VC dimension could be further increased, but your training error increases and the bound does not necessarily decrease. So we have explain why should we do this, right? This is essential trade-off between data training, data fitting, and the margin maximization, right? So this is overall SVM objective function, right? So now, to get a still form, we'd like to first convert it into a minimax optimization problem, right? From what we have just discussed. So to do that, remember each constraint will have a Lagrange multiplier, right? And from the general definition, the constraint is in the form of a constraint function less than or equal to 0, right? So if we want our SVM objective to be consistent, that means we need to add a minus sign in both fronts to change the direction of the inequalities, right? Then for each constraint, you're going to introduce a Lagrange multiplier. So for the function margin constraint, we'll introduce alpha I. And for the non-activity constraint for the slack variables, we will introduce Lagrange multiplier beta I. And then our Lagrange function will be the original SVM objective, is here, right? Plus a linear combination of those constraint functions. Remember, we need to put a minus sign in both fronts because it must be something like G1x less than or equal to 0, right? You need to change the direction of the inequality and move the right-hand side part to be the left, and so that the right-hand side is just simply 0. And then you do this linear combination of the constraint functions multiplied with multipliers, right? It will be this form, right? So this is a original objective function. These are the Lagrange multipliers multiplying with the constraint functions. Okay? And remember, we're doing minimax optimization. Okay? In the inner level, we do the maximization with respect to the Lagrange multipliers plus non-negative constraints. So Lagrange multipliers include alpha i's and beta i's. So we require that alpha i's and beta i's are non-negative, right? In the outer level, we maximize the Lagrange or minimize the Lagrange function with respect to the model parameters, which include the weight vector, the bias parameter, and the select variables. Okay. This is just a standard application of the minimax representation we just discussed. Okay. So any questions so far? Okay. Okay. So now we know that to get the dual form, we just need to switch the order of max min. Right? The Lagrange function doesn't change at all. Right? But in the inner level, we're going to first minimize the Lagrange function with respect to model parameters, including WB and select variables for CIs. Okay? And then in the outer level, we do the maximization with respect to non-active multipliers, alpha i's and beta i's. Okay? And according to the Slater's condition for convex optimization, the primal dual form have the same solution. That's basically what I just mentioned. Right? Because Slater conditions roughly can be saying like, okay, if you're doing a convex optimization and the feasible space of the variable you want to optimize at least have one interior point, then you can see that, okay, it satisfies Slater conditions, then the primal problem will be equivalent to the dual problem. Right? But anyways, these are not required for you to memorize. You just have some sense. Just need to know the solution, need to know the conclusion. Okay. So next we're going to look at how we solve this max min problem, namely the dual problem. Because the whole problem seems including both objective function and the optimization step, it seems pretty lengthy, right? You got two levels, you got a lot of variables you want to optimize, right? The Lagrange form, the Lagrange function of the objective, which is also quite complicated, right? So I want to simplify this dual optimization problem. How can we do that? How can we do that? So the idea is very, very straightforward. So this is my objective Lagrange function, right? So I want to say like, okay, can I reduce this max min problem to be just one level of optimization problem? Okay. How can we reduce it? Because this is max min, right? So let us assume, okay, in the outer level, I have already fixed the current alpha i's and beta i's. Can we directly solve the inner minimization problem? And I just substitute the optimal L with respect to WB and KCI's, right? And into the inner part. So I know the inner, what is the solution for the inner minimization problem, then the remaining step is just to do the outer maximization. Right? That's the idea. It's very, very straightforward, right? So then let us try to do that, right? And suppose we fix the outer level, right? That means I fix the current alpha i's and beta i's. Let's see what is the minimum value of L with respect to WB and KCI's. Right? Now, how can we do that? How can we get to the minimum value of L with respect to WB and KCI's? Any thought? It's still a minimization problem, right? If you want to get the minimum value of this function, how can we do that? Any thought or any guess? Yes, right? L is a function of WB and KCI, right? If I want to get a minimum value of L with respect to WB and KCI, the most straightforward way is just calculate gradient, right? And set the gradient to be 0. And that's it. And nothing special, right? But remember, because we kind of fix the outer level, that means alpha i's, beta i's are fixed, are viewed as constant, right? I only take the gradient of L with respect to WB to CI and set the gradient to be 0. I know that, okay, given the current alpha i's, beta i's, what kind of values of WB and CI can make L to be minimum. Right? That's the idea. So let's try to solve that, right? Let us try to calculate the gradient of L with respect to W, B, and every CI, and set the gradient to be 0 and see what we can get, right? This is actually is also pretty straightforward. It's just a practice of your calculus 1, I guess, right? If you take the gradient of L with respect to W, we know that the first quadratic term, the gradient of this term will simply be W, right? And there are only one term or one summation that includes W, which is here, right? So if you take the gradient with respect to W, because it's just a linear dot product with xi, so the gradient will be just xi times yi and alpha I. So if you solve the gradient of W with respect to W to be 0, you simply get W equals to the summation of alpha I times yi times xi. And that's it. Right? And then let us take a look at the second equation. You take the gradient of L with respect to B and set it to 0, right? So you know that B is only showing up here, right? So if you take its gradient to be 0, this will give you the summation of alpha I, yi's to be 0, right? Because the gradient of B is just the coefficient of B, right? Which is alpha I, yi, and you just do the summation, right? If you set the gradient to be 0, it's simply this summation to be 0. And if you take the gradient of L with respect to each slack variable, Ci, you see that Ci shows up here and shows up here, right? And if you set this gradient to be 0, it just tells you that for every pair of alpha I and beta I, their summation must be C. So this is a really straightforward to derive. So I'm not gonna derive here, but I encourage everyone to manually check this. Right? Okay, so we know that when we get L, the minimum of L, we must have these 3 equations to satisfy, right? So let us replace or substitute those results back into L and see what is the value of L we can get, right? If you're doing this, right, you can immediately simplify the form of L to be a quadratic function with respect to alpha i's only. Okay. This is pretty straightforward as well, because you see that because all the coefficients for B, their summation must be 0. So you can see that all the terms multiplied with B will be simply 0. And because the gradient with respect to each Ci to be 0, that means the summation of the coefficients of Ci must be 0. If you substitute back, these terms that relate to Ci's will cancel as well. And then when you substitute the summation form for W, right, you'll get a quadratic form with respect to alpha. That's how we get this new objective function, which is the minimum value of L with respect to WB and CCS. Okay. But again, I highly recommend everyone to manually check this result. Okay. And meanwhile, we need to be clear that the minimum value of L, which is here, is obtained only when all these 3 equalities hold, right? So that means you need to respect that this equality and this equality is satisfied. That's why when we simplify it, right, we need to also add these 2 constraints, right, because it comes from solving the inner minimization problem. And then we can reduce our maximum problem into one level maximization problem, right? This maximization problem is only for the Lagrange multipliers, alpha i's, beta i's, in the outer level, right? Because in the inner level, I have already known what is the minimum value of L with respect to model parameters, right? But meanwhile, because this minimum value is achieved when those inequalities hold, those equality holds, those equality come from the gradient to be zero. So I have to respect this equalities as constraints. Right? So in this way, we get a simplified form of our dual problem for SVM. So we can see that to solve the dual problem, all we need to do is just solve a one-level constraint optimization problem with respect to the Lagrange multipliers alpha i's and beta i's. Okay, any questions so far? Okay. This one? Is here. You see -1 here. Yeah. Any other question? Yeah, again, I'm just trying to give you the logic. I'm not exposing every detail because I believe that's simple for everyone, right? But I still encourage everyone to manually check this, right? How we derive at this step. Right? Is everyone comfortable at the current result? Okay, great. So let us continue, right? Now our task is to solve this maximization problem, right? First, we find that beta i's do not show up in the objective function, right? It only shows up in the constraint. So can we further simplify this problem to get rid of beta i's? It's actually pretty simple because we know that alpha I and beta I both are non-negative, right? And their summation must be C. So you want beta I to be, that means beta I is simply C minus alpha I, right? And meanwhile, because you want beta I to be non-negative, that just means C minus alpha I to be non-negative, right? Then you can simply get rid of beta I by constraining that alpha I must be less than or equal to C, right? If you don't say it that very straightforward, I can. Because from the constraint, we know that beta I, once you know alpha I, you know beta I, because beta I is simply C minus alpha I, right? And you want beta I to be non-negative, right? This is our basic constraint, right? Then you just require that C minus alpha I to be non-negative. That just tells you that alpha I must be less than or equal to C, right? And then you can just throw out beta I because it never appears in the objective. So then we can further simplify our dual problem by only optimizing alpha I, right? And alpha I, from here, we know that first, you must satisfy a linear constraint. That is the summation of all alpha I y i's to be 0. Second, each alpha I must be bigger, no less than 0 and less than or equal to C, right? And third, the maximization problem can be equivalent to doing a minimization problem as long as you just put negative sign in front of the objective, right? So now we come to our final dual form of SVM. Right? Essentially, we're trying to solve a quadratic optimization problem with respect to alpha I only, and with respect to subject to some constraints over alpha I. Those constraints are every alpha I must be between 0 and C, and there is a linear constraint. That is the combination of alpha I and y is simply 0. Okay, so how to solve this problem? This is standard convex optimization problem. It's called the quadratic optimization problem. That means we actually do not need to worry about how to solve that. There are a lot of very mature and fast optimization package that can solve that. We don't need to worry about that. Okay. So that means as long as we derive such a form, right? We can call any off-the-shelf quadratic convex optimization package to solve that problem, right? And then the question will be, okay, why do we bother to solve this dual form? Why would we get rid of the original model parameters in the primal domain, including WB, the CIs, right? We just optimize these Lagrange multipliers alpha i's. So as we will see later, right? This objective form will enable the so-called kernel trick and nonlinear classification in infinite dimensional space. Okay. So previously we said that, okay, if we want to generalize our linear classifier to classify nonlinear, to do some nonlinear classification, how can we do that? We want to perform some feature mapping, right? Nonlinear feature transformation to lift the feature dimension to a higher dimensional space, right? And you will see that in some cases, you might want to lift the feature dimension to infinite dimensional space. In that case, it won't be explicitly computed, right? Because you're not, in practice, you will never be able to compute infinite dimensional feature vector. And to avoid the explicit feature mapping computation, we want to use the so-called kernel trick. And the kernel trick, as we'll see later, is just to help you compute the dot product of two infinite dimensional feature vectors in the original feature space. That means you never need to really compute what is the feature mapping it is. You just compute the kernel function in the original low dimensional feature space. It is equivalent to first do the feature mapping and then do the dot product. Right? And then the dual form enable us to directly inject a kernel trick here to replace the dot product by a kernel function. But we'll see that later. But right now, let us first consider another problem. Right? So after a series like mathematical derivation and the simplification, we get this dual form, right? We solve that, we know that it is equivalent to solving the primal form. But the problem is once we have obtained the optimal Lagrange multipliers alpha 1 star to alpha n star, how do we recover the optimal W and B? After all, our classifier is determined by WB rather than this Lagrange multipliers. So the natural question will be, okay, once I got Lagrange multipliers, alpha 1 star to alpha n star, can we use that to compute or to obtain the optimal weight vector and the bias parameter? That is our question, right? So how can we do that? Any thought? Yes. We just need to look back at what we have derived to simplify this optimization problem, right? If we're going back, right, we know that when we solve the inner minimization problem, we take the gradient of the Lagrange function with respect to W and set the gradient to be 0. This have already told us that W must be a summation of alpha I, y, xi's, right? So now you know the optimal value of alpha 1 star to alpha n star. You just substitute for alpha I. You get optimal weight vector W star, right? So you can see that W star is just a weighted summation of every training example. Okay. And be careful, alpha star has important meanings, which we're gonna see later. Yeah. Okay, so from the inner minimization procedure, right, we just derived, we know the relationship between W and alpha. And once we get optimal alpha, which is substituted into that relationship, we get optimal W, right? Then the remaining problem is how do we get the bias parameter B? Unfortunately, you cannot recover the optimal B just through your previous derivation. The reason is that in our previous derivation, we set the gradient of B to be 0, right? And the gradient of B doesn't contain B at all because it's a linear term. It's something multiplied with B, right? You take the gradient with B just get rid of, right? And you cannot use any of those intermediate conclusion to derive the optimal B. Now how to get B? To recover the optimal B, we have to introduce a little bit more knowledge about the optimization theory. We're going to introduce the so-called Karush, Krug, Tucker conditions, named as the KKT conditions. How many of you have heard of KKT conditions? How many of you have taken any optimization class before? Okay, KKT conditions serve the key point or the core of the optimization theory. It tells us when we can conclude you find an optimal. So what are KKT conditions, right? KKT conditions basically are a set of testing conditions. Given any any setting of variables, right? You want to test if this optimization variables satisfy these KKT conditions, then you can draw a conclusion whether you have arrived at local minimum or local optimum. Right? So let us look at what are KKT conditions, right? So here we're just talking about KKT conditions for convex problem or constrained convex problem. So there are general KKT conditions, meaning that for any constraint optimization problem, what are KKT conditions, right? So here we only focus on convex program because we're focusing on SVM, right? SVM is a convex optimization problem, right? So suppose I have such a convex optimization problem where I want to minimize a convex objective f0x, and meanwhile I want to x to satisfy big M constraints, where each constraint is written as f1x less than equal to 0, f2x less than equal to 0, blah, 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 until f big mx less than equal to 0. Okay. Then suppose I find a pair of x and lambda. So you can see both x is has the same dimension of the optimization variable I want to optimize in the original problem, which is just n-dimensional. And lambda has a dimension which is equal to the number of constraints. Okay. So I given x and lambda, I compare x lambda. So I want to look at if this pair of x lambda satisfy 4 groups of testing conditions. Okay. Those are KKT conditions. So the first group is just to test if x satisfy those M constraints. That is, you just want to check if every constraint function over x is less than or equal to 0. Right? And the second group of testing conditions just to test if lambda is non-negative. Namely, every element of lambda is non-negative. And third testing condition is very interesting. Okay? This is called complementary slackness. It just tests if the product of lambda m and the corresponding constraint function value on x is 0. Okay. So you could see that at least one term will be 0, right? Lambda m is 0, or the constraint function is 0. Right? This is called complementary slackness. Right? The last one is just to test if the gradient of the Lagrange function at x and lambda is 0. Right? Because this is just Lagrange function take the gradient with respect to x and lambda. Right? Okay, so those 4 groups of conditions are called KKT conditions. And you can test any pair of x lambda to see if this pair of x lambda satisfies KKT conditions. Does it make sense? Okay. So if your pair of x and lambda satisfy these KKT conditions, what conclusion can we draw? Okay. Here are the conclusions. If you find a pair x star and lambda star which satisfy the KKT conditions we just mentioned, right? Then we can conclude that we can conclude that X star is a solution to the convex program here. And this is called sufficient condition. Meaning that, okay, as long as you can find a pair of X star and lambda star who satisfy all these four groups of conditions, they can conclude that X star is one solution of this problem. However, it's not a necessary condition, meaning that there could be some solution of this convex optimization problem for which you don't have a corresponding lambda which satisfy all these KDT conditions. So it's just a net sufficient condition, it's not a necessary condition. This is a general case. However, if you can restrict the type of constraint functions, you can make KKT conditions to be both sufficient and necessary. In detail, if your convex optimization problem, the constraints are affine constraints. Namely, you can represent your constraint as a linear inequalities. Right? So this is a vector. Ax is vector, B is vector. Right? If you can write your constraints in this way, then KKT conditions are both sufficient and necessary. More specifically, if you can find X star and lambda star which satisfy the KD conditions, of course, X star will be the solution, right? If X star is the solution itself, then you must have a corresponding lambda which satisfy the KD conditions. So you can go from A to B and go from B to A, right? And it forms a closed loop. Okay. Those are just the conclusions, okay? And you can find any optimization book, it will give you the proof for this, right? But we don't need to care about the proof details. We just want to know what are the results, right? So now we can take a look at the form of SVM. Right? We can conclude that for SVM, KKT conditions are both sufficient and necessary. Why? We just look at constraint form, right? This is a constraint form. Right? Regarding WB and KCIs, they're just linear constraint functions, right? In other words, it is straightforward to manage or organize the constraint in this form, in this affine form, right? Yeah, if you feel uncomfortable, try to organize the term by yourself, right? And try to construct what is A and what's B here, right? It has such a form. Then it means that your constraint is relatively simple. And so the KKT conditions are both sufficient and necessary for the solution of your SVM objective function. Does it make sense? Any questions so far? Why is it so important? Because as long as we know that, okay, for any solution of SVM, it must satisfy the KKT conditions, then we know additional knowledge between those optimum variables, right? You can use those conditions to infer what is the optimal value of the bias parameter. That's why we introduced the KKT conditions. We're on the same page, right? Okay. So now, since we know that for SVM, right, because the constraints are affine constraints or linear constraints, we know that for any solution, you can find a corresponding Lagrange multipliers. The solution namely the optimal model parameters and the Lagrange multipliers, they will satisfy the KKT conditions. Right? So then we're going to leverage these KKT conditions to infer what is the optimal bias value B. Right? So which KKT conditions we're going to use? We're going to use this complementary slackness. So remember the KKT conditions, it contains 4 groups of testing conditions, right? And this one is called complementary slackness, namely the product of each Lagrange multiplier with its constraint function is 0. Right? Applying this to the SVM case, this is a constraint function, right? So constraint function will be just a function margin minus 1 plus KCI, right? And it multiplies its product with the multiplier should be 0. Okay? And similarly, this is another constraint. The constraint function is simply minus KCI, right? Then when it multiplies the Lagrange multiplier beta I, the product must be 0, right? This is the complementary slackness of the KKT conditions. We know that at optimum, they must satisfy this. Right? This is what the theory tells us. Does it make sense? Right? It just apply the KKT conditions over the optimal values of those model parameters and the Lagrange multipliers. And then let us try to combine the intermediate results when we solve and simplify the dual form with this complementary slackness and see if we can derive B. Right? And we're going to use this result, namely in the inner minimization level, the gradient of the Lagrange function L with respect to each KCI is 0. That just tells us that the summation of each alpha I and beta I is C. Okay? So now we get 3 pieces of results, right? The first 2 comes from the KKT condition, more specifically complementary slackness. That is the optimal beta I times the optimal KCI is 0, every I. And the optimal alpha I times the function margin subtracted by 1 plus the KCI is 0. Right? This is a direct application of the KKT condition over the optimal Lagrange multipliers and model parameters, right? And third one is when we solve the dual form, we know that alpha I star plus beta I star must be C, right? Then the remaining task is just to combine these 3 solutions and see the 3 results and see how we infer the optimal bias parameter B. Okay. I'm going to do that, right? Okay. So I just list or copy the results here, right? Now, let us try to find some example J where the optimal multiplier alpha G star is strictly between 0 and C. Right? Remember, when we're solving the dual form, we only get the optimal alpha G's, right? I just look for those alpha G's, right? And find one whose value is right between 0 and C. That means it doesn't equal to 0, it doesn't equal to C. It's right between 0 and C. And let's see, according to those results, what can we get, right? So first, because alpha G star is less than C, then we know that the beta G star will be strictly positive, right? Because beta G star is C minus alpha G star, right? So beta G star is strictly positive. Then according to this complementary slackness, we know that the optimal slack variable correspondingly is 0, right? Because this product is 0, right? Then this guy is positive, then this one must be 0. So we know that, okay, the KC G star must be 0. And then because alpha j star is strictly positive. That means this guy is positive, right? Then this term, the constraint function must be 0, right? Because their product must be 0, right? One guy is non-zero, then the other guy must be 0. Then we can get that, okay, this constraint function is 0. And meanwhile, because we know that the CG star must be 0, so you know that, okay, this guy must be 0, then that means the function margin must be 1. Right? And then because W star has already known, right? We have already known W star. We know that it's just weighted summation of the training examples weighted by these alpha G stars, right? You know W star. Then from this equation, we know that B star will be YG subtracted by dot product between W star and XG. Then in this way, you got the optimal B. Any questions so far? Does everyone feel comfortable? Okay. If you didn't catch up this logic, the reasoning, it doesn't matter. You just look at the 3 conditions and follow the slides. It won't take too long time to know why. Okay. So in practice, you might have multiple J's whose alpha J star is right between 0 and C. So to be robust, like we usually average the results over such J. Right? Then in this way, you got B star. So any question regarding it's not always guaranteed, but in most cases it will be guaranteed. Right? I mean, in the extreme case, say alpha J star all C, which is unlikely to happen in practice, you can going back to primal form because you know the W star. And you can going back to the primal form to solve the optimization problem only with respect to B. Right? That's the one. That's the the most general approach of doing that. But if you can find one alpha G value is right between 0 and C, then you can get B. You don't need to rerun optimization. Any other question? Okay. Again, I highly suggest everyone to reason this result, reason under these conditions and get the result by yourself, right? To deepen your understanding. Because we won't take some exam to ask you guys to derive this, right? But it is very important, very important for you to understand how we get the result. Because when you solve the SVM, okay, you just call maybe one library, one line of code to solve that quadratic optimization problem. But we do need to know how we arrive at quadratic optimization problem. That's the key. Right? Okay. So now let's go back to the structure of W star. Right? From the dual form, we know that when we solve alpha J's, right, we can obtain the optimal weight vector as the weighted summation of all the training example, where each training example is weighted by this alpha J's or alpha I's, right? Then what if some alpha J's are simply 0? If one alpha J is simply 0, that means that corresponding input vector or training example doesn't have any effect on the optimal weight vector, right? In other words, the final weight vector is only determined by samples with non-zero alpha J star. Right? In other words, the optimal weight vector might only be up to a subset of training examples whose corresponding multipliers alpha G star is non-zero. Okay. So we call those subset of examples as support vectors. That's how this support vector machine comes from, how this name is invented. Because the final weight vector is only determined by a subset of training examples. And those subset training examples can fully determine what is the weight vector. And we call this subset examples who determine weight vector as support vectors. So where do the support vectors locate, right? Where are those support vectors? That's something we're interested in. Which examples can serve as support vectors? Which examples are not support vectors? Let us try to further our analysis. Right? So we know that a support vector, its alpha G star must be positive, right? According to the complementary slackness, we know that alpha G star multiplying the corresponding constraint function, which relates to the function margin, must be 0. And this guy is bigger than 0. That means this guy must be 0, right? This guy is 0 just means the function margin is 1 minus c G star. And this guy is less than or equal to 1. Right? Because the function margin is 1 minus c G star. And c G star is not negative. It just means, okay, the function margin is less than or equal to 1. And remember, an example is outside margin only when the function margin is bigger than 1, right? If the function margin is less than or equal to 1, it just means this example stay on or inside margin. Right? Then our result tells us, our analysis tells us support vectors must be on the margin or inside margin. That's where the support vectors come from. Actually, for those examples which are far away from margin, they'll never determine the weight vector. Right? That's very interesting, right? So for those examples which break into the margin, or at least on the margin, those bad points or outliers actually determine what is your final weight vector it is. Right? For those very super good examples which are far away from your classification boundary is outside margin, they have nothing to do with the weight vector. That's an interesting conclusion from our analysis. Right? And also, I leave you guys a question like, what if a support vector stays inside the margin? Right? That means, what if your CG is strictly bigger than 0? If it is strictly bigger than 0, according to the complementary slackness, you know that this guy is bigger than 0. Then this beta G star must be 0, right? And then this guy must be 0. That means alpha G star must be C. So that means alpha G have reached its upper bound. So this is another interesting conclusion we can analyze, right? Okay, so now we want to give a visualization about support vectors, right? So suppose these are the positive and negative examples, and we train our support vector machines, and we find a classification boundary, which is black line here, and a margin here, right? And you will see that the support vectors will just, those examples stay or inside margin. And for those examples which are outside margin, which means that they're far enough from the classification boundary, they are not support vectors, and their corresponding alpha I stars is simply 0. In other words, the learning result of support vectors actually have many examples whose alpha G stars or alpha I stars is simply 0. Okay. And the W star is only determined a small portion of the examples in the data set. Okay. And to get W star, we're only to store this small portion of training examples. Okay, any questions so far? We're on the same page, right? Okay, great. Next, we're gonna start talking about kernels and kernel tree. And so continue with the dual form of SVM, right? When you make a prediction, right? We know that given X, right? I want to calculate dot product between W star and X, and plus the bias parameter B, which we can also recover from the dual solution, right? We know that W star is a summation, a weighted combination of the training examples. More specifically, it should be a weighted combination of the support vectors. Right? Then, if we substitute this form back to our classification function, we know that the dot product between W star and X will be in this way, right? Or we just the weighted summation of the dot product between every training input vector and the test input vector, and weighted by alpha i's. In other words, we actually do not need to really compute W star. We just need to compute dot product between the training examples and new example and do a weighted summation. And that's it. So now let us consider our nonlinear classification strategy. Right? We mentioned before, like if we want to perform some nonlinear classification task, we would like to first map our original feature vector or input vector to some higher dimensional space. Let us denote by the mapped feature vector by phi xi, right? Then you can imagine after the feature mapping in the higher dimensional space, you can train a soft SVM, right? Your optimal weight vector in that space will still be a linear combination of the mapped feature vectors, right? In the higher dimensional space. Then you calculate the classification score is still in this way, right? The dot product between W star and the mapped feature vector, which is just a linear combination of the dot product between every mapped feature vector phi xi and phi x. And phi x can be whatever feature mapping you choose, right? So now let us look at the dot product here. We can see that during the prediction phase, we only need to care about the dot product between mapped feature vectors X and Z. So let us define this dot product as a function of X and Z. Okay. So it's a function of two inputs X and Z, and the result is to obtain by first do the feature transformation over X, and then do the feature transformation over Z, and then do the dot product. Right? And then the prediction with this high dimensional lifting map can be written as a weighted summation of the kernel function of every xi and x plus the bias parameter b, right? And this is obtained by just derive the form of representation of W, right? And then do the dot product between W and map the feature vector phi x, right? So why would like to give this form, right? I would like to give this form. If we just want to give a notation sugar, actually does not bring any benefit, right? Because computing K is equivalent to first do the feature mapping and then do a dot product, right? There's nothing meaningful in practice. However, if we can invent a new computation tree such that I can cheaply compute this K function without explicitly performing feature mapping and dot product, then this will be very useful, right? Why should we bring this problem? Because from our simple example, we just lift the feature dimension from 2-dimensional to 4-dimensional. That seems all right, right? But in complicated problems, the feature mapping is really very, very high dimensional. It's not just like the original problem is 10 dimensional, just leave it to 20 dimensional. It's not like that. It can be you lift your dimension to 1 million dimensional or even infinite dimensional. In that case, it is practically infeasible or computationally too costly to directly compute the feature mapping and do the dot product, right? Especially in the case that infinite dimensional mapping, you will never be able to compute an infinite dimensional mapping in practice, right? You have to seek a workaround, right? Can we compute this K function directly rather than performing the feature mapping and dot product explicitly? Right? If we can do this, this is called kernel trick. So to explain the kernel trick, right, we want to start with an example, right, concrete example, which is called polynomial kernel. Right? Suppose we're given two examples, x and z, right? This example, I mean, input examples are just n-dimensional, so it contains n elements, x1 to xn, right? I'm gonna do a feature mapping according to a polynomial, right? According to a second order polynomial. Right? How can I do that? Right? This is definition. Right? It just lists the zeroth order polynomial, which is simply 1. And then first order polynomial, x1 to xn. Then second order polynomial, which is just the square of x1, x2 to xn squared, and also all the cross product between those features. Okay. So yeah, our feature mapping, right? You know, our mapped feature vector, it contains all degree 0 terms, all degree 1 terms, and all degree 2 terms. Right? So now I want to ask, what is the dimension after you perform this feature mapping? So original, the feature vector is n-dimensional, right? So after the feature mapping, what is the dimension of the feature vector? Yeah, we can just count, right? So all degree 0 term is 1, right? All degree 1 term is n. And how about all degree 2 terms? It's just n times n minus 1, right? And perhaps you have to divide it by 2, right? But overall, you know that after the feature mapping, you got O(n) squared dimension, right? Like imagine your n is 100. Then after this feature mapping, you got 10 to the power of 4 dimensional feature vector, right? And then I want to compute the dot product because I want to do the, the prediction, right? I want to compute dot product of the feature mapping between every training example and the test example, right? So to compute dot product between any mapped feature vector, the time complexity will be O(n) squared, right? Because after feature mapping, the dimension of mapped feature vector will be O(n) squared, right? If you do the dot product, that means just analyze product and summation, right? It will take O(n) squared. That is pretty costly, right? From our previous example, like suppose n equals to 100. After the feature mapping, you got 10 to the minus 4 dimension, right? And you compute dot product between two super long feature vectors together. It is costly. Right? And is there any way to avoid or to reduce time complexity? So here we can choose an alternative approach. Right? I can define kernel function. Right? And the kernel function compute the value in the original space, which is simply doing the dot product between x and z plus 1 take square. So what's the time complexity to compute B? Any thought? X and z are both n-dimensional. So if you want to compute this function, what's the time complexity? Yeah, O(n), right? Because x is n-dimensional, z is n-dimensional. The dot product, just do n itemwise product and the summation is just O(n), right? And then plus 1, is constant operation. I take square constant operation. So the computation of the function B is very cheap. It's O(n), right? So now I want to claim that A equals to B, or A is equivalent to B. So basically, computing B is equivalent to first performing this quadratic feature mapping explicitly, then do the dot product. That's my conclusion, right? If we do the explicit feature mapping and then do the dot product as we show here in A, right? The time complexity is O(n) squared, right? However, if we directly compute this function, the time complexity is just O(n). If they are equivalent, of course, computing B is much, much cheaper and fast, right? That's the benefit of using the so-called kernel trick. Okay? Kernel trick just means if I can compute the kernel function in an alternative way, and it is still equivalent to performing the explicit feature mapping the dot product. Okay, next step, I'm going to show that why calculating A and calculating B is equivalent. Okay. Let's stop here today. Let's stop early here today, okay? Because if we want to write down all the terms here, it'll be quite lengthy. I guess 5 minutes won't be sufficient. Okay? But let's just keep this in our mind. Right? This is just a concrete example showing that how kernel trick is useful. It can avoid you to do some very costly feature mapping dot product computation. You just compute everything in our original feature space to save your cost. Okay, yeah, let's stop here today. See you on next Tuesday.